Hello guys, welcome back to my channel Gamma Digamma. Today I'm officially starting the calculus sequence. So I'm going to do limits. I'm going to try to give you an intuitive understanding of the concept as much as I can. Hope you guys enjoyed. So for some of you that read my blogs, I've already written a blog on the topic. So this video will cover the essential part of it, and since I'll be drawing graphs and stuff, it will be helpful for you guys. Okay, to start with, we have a function, say f of x equals x squared minus 1 over x minus 1. And with calculus, the story always starts with a function. And now, I'm so jobless, I want to find the value of the function at 1. I need to find f of 1. Now, if you substitute 1 over here, you get 0 over 0, which is undefined. And even when you look at the graph of this thing, let me just graph it on the side. It's not to scale, obviously. So here's say minus 1. And this is a plus 1 line like this. Say this is 1. So that's basically what the graph looks like. Now, if you see, there is like a discontinuity over here, like an undefined region at x is equal to 1. That's why we were having this 0 by 0 problem. Now, I want to find a way to estimate what really happens at this point. Like the real value of f of x at say x is equal to 1. I mean, we can't get an exact value, but we can almost try to get an approximation. So, we can always extrapolate from what happens around this region. We can take values which are really close to 1 but like less than 1. Say f of say 0.99. When I substitute that, I get back 1.99. Okay, let's be even more close to 1. 0.999 equals I substitute that, I get 1.999. And okay, this was for x which was really close to 1. Now let me try to do that with x that is greater than 1, slightly, only very slightly greater than 1. So 1.01, I substitute that in that f of x, I get 2.01. When I substitute of 1.001, I get 2.001. And now looking at values slightly greater than 1 and values slightly lesser than 1, it's a great assumption that f of 1 is really close to 2. Now let's logically build up on that. Say I have h is equal to 1 plus x dash, and x dash is is like really close to 0 but not exactly 0. Okay, so h, when say x dash is like positive, we have numbers which are slightly greater than 1, only slightly greater than 1, numbers of this type. And once say x dash is say negative, we have numbers like this, very slightly less than 1. And I'm going to plug this in this original function and try to estimate something. So f of h equals 1 plus x dash the whole square minus 1 over 1 plus x dash minus 1. Now when I simplify that, I'll expand the bracket. 1 plus 2 times x dash plus x dash squared minus 1 all over x dash, because the 1 and minus 1 cancel out. And this cancels out with that negative 1. And since x dash is very close to 0, x dash is not 0, I repeat, x dash is not 0, that's why we can divide the numerator by x dash. Because if it was 0, we can't divide by 0. I hope you know that. So I have 2 plus x dash. Now since x dash is really small, its weight, it doesn't add much to 2. So we can reasonably approximate rather, that this is equal to 2. This is so small, we don't care about it anymore. Sorry x dash, but we don't care about it. And this is basically the logical way how we should think about limits. We are really close to something, because in our universe, division by 0 is not possible, and when I directly substitute, we have 0 by 0. But there is a way that we can, surpass this discontinuity. We can bypass this discontinuity by, extrapolating from points from x which is really close to 1 on both sides. So when x is only slightly greater than 1 and when x is only slightly lesser than 1, taking information from those points, we can see that it's really close to 2. And so we built on that by this is just a logical way of taking values which are really close to 1, and then we have a very good approximation of 2 clear from this data too. Now the way we proceed with this say mathematically is we call being really close to 1 as the limit as x tends to 1 of x squared minus 1 over x minus 1, f of x basically. So now, since we are really close to 1, we are not equal to 1. I repeat, we are not equal to 1. So, if we were equal to 1, you would just substitute and that, we get an indeterminate form of 0 by 0. So, we're really close to 1, and then we can use this difference of squares identity on this over x minus 1. And since, x is not equal to 1, we can just cut it out, because if it were equal to 1, it would be 0 by 0. Not possible in this universe. So now we have the limit as x tends to 1 of x plus 1. This is 2. Because now we are like, really close to 1. So a reasonable approximation is 2. That's I guess how you will be taught to evaluate limits at school or any limit course that you do, any calculus course that you do. So I'll just write that this limits are always good approximation, because it's the function as you saw in the graph wasn't defined. So it's a good extrapolation, a good an excellent approximation. Now to further build on the concepts, I'll give you another example function. Say g of x. It's a piecewise function. So x squared minus 1 upon x minus 1 when say x is not equal to 1 and 1 otherwise. So that's my piecewise function. Now let's just graph it over. Sorry if the lines aren't straight, but please bear with me. There's negative 1 here. There's 0. And there's 1. Line's gonna pass through minus 1 and 1. Discontinuity. This is basically 1. But like because of our definition, this point, because when x is equal to 1, f of x, g of x is just 1. Just label this g of x versus x. Yeah, so I wanted to make the point that although the function is say defined, I know it's not continuous. There's like a removable discontinuity, for some of you that may have done limits and discontinuities and just were needing a revision, you might recognize this as a removable discontinuity. So this function is defined everywhere. I mean it's 1 at x is equal to 1, but when I take the limit as x goes to 1, it's going to be this. It's going to be this 2 and not this 1, although it's defined, because limits are basically extrapolation from around this point. Say if I were to find if there were like a discontinuity over here and I needed to find information about this point, it would not be possible because there's only one side available. We can only extrapolate from this side and not there's like function ends over here. So the limit doesn't exist at this point because you need both sides. And I'm going to build on the concept of LHL and RHL, the left hand limit and the right hand limit, by the end of the video. And yeah, I'm going to give you another example question just to explain another concept. Now here's another example function. Say h of x is equal to, again, piecewise. You get used to a lot of piecewise functions eventually. X is less than or equal to 0. And say x minus 2 when x is greater than 0. Okay. Now, before doing anything, let's just graph it out. Like the negative half is gonna go like this. Extend this. Sorry. Straight line is really hard to yeah. This is like minus 2 like -1, basically h of x versus x. So it looks something like that. Now here I would like to introduce the concept of the left hand limit and the right hand limit as I promised earlier. So, okay, so I'm gonna find the limit as x goes to 0. But I want something else. I mean, I want more information. X goes to 0 from the negative side. So x is basically going from minus infinity, then it's really getting close to 0, but not at 0, but it's still negative, right? So like the top half of h of x will be used to calculate the limit, and when I just substitute 0 in, yes, wait, let me just write it out first. The essentially limit as x goes to 0, x squared minus 1. So when I just substitute 0 in, there's no problem at all. So when I'm like really close to 0, but from like the negative side, it's minus 1. It's pretty close to minus 1, and minus 1 is a reasonable assumption, and a really reasonable one in this case, because the function is continuous, right? Like there's no like a circle of discontinuity like we had in f of x. So okay, this is what we call, write it down here, LHL, the left hand limit, because we're approaching 0 from the left side. And there is also something known as RHL, right hand limit. So the limit as x approaches 0 from the positive side. So from like values greater than 0, like we're really close to 0, but like on the positive side. In contrast to RHL, which was just for values lesser than 0, really close to 0, but like less than 0. H of x. So now I'll have to use the case where x is greater than 0. So like the bottom half of h of x. Limit as x approaches 0 from the positive side of x of minus 2. I can just substitute again. It's continuous over there. It's minus 2. We call this the RHL. But now notice that LHL is not equal to RHL. LHL is not equal to RHL. So like like I said before, we needed to extrapolate from both the sides, from the positive, like from values less than the point concerned and values slightly greater than at the point concerned. We needed both of that information for extrapolation, for getting a good approximation. I mean, we used 0.99 and 1.01 for being very close to 1. I mean, we needed both halves of it, like values less than that point and slightly greater than that point. But since like both of them they disagree, like the limit in general of h of x does not exist. So here's another kind of concept. So a limit does not exist if the left hand limit is not equal to the right hand limit. I mean, then the general limit does not exist. A few more examples to like really drive the point home. So the limit as x approaches 5 of 24. Now it's just a constant, no x, it does not depend on x, so it's just 24. Limit as x tends to 7 of x plus 2. Now it's just continuous, it's a linear function, it's continuous, and when x is really close to 7, we can just, it's a really good assumption to just plug in 7, and 9 is a pretty good approximation. The best one in this case, because it's continuous. And say you have a function like x approaches 0, 1 over x. Now whatever you do, 1 over x is like this. When you are, say, firstly looking at it, and I hope you understood what LHL and RHL are. Like the LHL will give you like negative infinity and RHL will give you positive infinity. So in any case, the limit as x approaches 0 in general does not exist. But even if we were to substitute something, it just diverges, because like when x gets really small, the whole fraction gets really large, and it basically tends to infinity. This thing tends to infinity. Plus minus, it just depends on LHL, RHL. So this limit diverges. There's no way we can get a better approximation. It just diverges. It doesn't exist. So another one, last one, limit as x approaches 0 of the sine of 1 over x. Now when we plug in 0, it's just sine of infinity, and if you know how sine operates, sine's just up and down, up and down, up and down, it just oscillates. So even if we were to grow, like even if like say x were to grow a lot, sine won't reach like a definitive value, like for example in this case, if x were to approach infinity, it eventually tends to 0. But like over here, there's no certain value that the sine would take, as x gets really large. It just keeps oscillating between -1 and +1. So this limit doesn't exist. I don't think you necessarily need to check whether for the LHL and the RHL. It just doesn't exist. It just keeps on oscillating. So guys, I hope you guys understood. I tried my best to explain. I know this video has been the longest one I've ever recorded. But in the next video, I'm going to be exploring, probably solving some basic limit questions, using some properties of limits, and then in the future I'll be doing a video on continuity, because LHL and RHL continuity is basically building up from that. So I hope you like